All right, guys, so we finally get to an example for using the node voltage method. So this is still section 4.2. This is on the node voltage method. But finally, we get an example. Now, the circuit that we're actually considering is a circuit that contains both voltage and current sources. So how the node voltage method handles these types of sources is somewhat different. Um, However, the circuit only contains independent sources, no dependent sources. So this is a circuit that contains only independent sources. And in this case, we have both a voltage source as well as a current source. Now, the circuit that we have looks like the following. There's an independent voltage source providing us with 10 volts. It is then hooked up to a network of resistors at the top here that look like this. Oops. And then at the very end, over here, we have a current source, providing us with 2 amps going up this way. Down this branch, we have another resistor. And down this branch, we have yet another resistor. And then the circuit is complete, like this. This is a 1 ohm resistor, a 2 ohm resistor, a 5 ohm resistor, and lastly, this is a 10 ohm resistor, like this. Now, the question is to find the current in the 2 ohm resistor. And we're going to use the node voltage method in order to do that. Now, first things first, let's go ahead and identify all of our nodes. There's a node here that's easy to miss. There's a node there. There's a node here, like this. And there's one large node here at the bottom that looks like this. Now, we need to choose one as the reference node. And I would suggest, in general, unless you have a good reason to choose something otherwise, and sometimes there are good reasons for it, I'm going to choose this bottommost one as the reference node. Now, the reason for it is relatively simple. Notice that this node contains the largest number of elements. Now that we've chosen our reference node and assigned it a node voltage of 0, we need to then label our independent nodes. This is where our variable names are actually going to come in. Right? Now, the way we're going to do that is we're going to take a look at voltage sources. Notice that there is a voltage source right there. Right? That means that this node up here is not an independent node. The node voltage at this node is the voltage rise from the ground node up to that node in question. So when I move up this way, like this, notice that I am going through a voltage rise of 10 volts. That means that the node voltage at this node is 10 volts. Now, there are no more voltage sources. That means that whatever nodes are left, they are independent nodes. I need to give them variable names like this. So I'll call this node A, I'll call this VA, I'll call this node B, and the node voltage is VB. That takes care of the next step. So notice that this node over here doesn't get a variable name. Why? Because there's a voltage source there. Now what I'm going to do is at the essential nodes, I'm going to write down KCL and use the modified version of Ohm's law to write down a system of equations. And I'm going to assume that all of the currents at each one of the nodes is going out, right? So here, I'm going to begin, in terms of setting up a system, I'm going to use KCL at node A, which means that the sum of all of the currents flowing out of this node must add up to 0 at node A. So over here at node A, I am assuming that there's a current going this way, a current going that way, and a current going that way. Now again, these currents are fictitious currents. They're used for bookkeeping purposes, right? And as long as you stay consistent with that convention, you can write down equations. I'm also going to use the modified version of Ohm's law in order to write down what those currents are. So the current going from this node through the 1 ohm resistor out to the 10 volt source there is something that I can write down. And in terms of the modified version of Ohm's law, that current is VA, the node where the current starts, minus the voltage of the ending node, that is 10 volts, all divided by the resistance that it's going through. That's 1 ohm like this. That means that this current here is this term. Doesn't look like a current, but it is a current. Then I'm going to concentrate on this current. This current is starting at this node, it is ending at that node, and is flowing through the 5 ohm resistor. So I can say that it is VA minus the ground node divided by the 5 ohm resistance. I'm just going to repress the ohms for now, just write it as 5 like this. So here, this term corresponds to this current. Lastly, I have this current to contend with. It is starting at the node A. It is ending at the node B. It is flowing through the 2 ohm resistor. So I can say that this is VA minus VB over the 2 ohms. Those are the only 3 currents that exist at node A. So the sum of those currents must add up to 0. Now, this itself is an equation. It's not in standard form. Let's go ahead and clean it up. I'm not particularly fond of all of these fractions, so I'm going to get rid of them by multiplying by a common denominator of 10. I'm going to distribute and collect my terms. So 10 divided by 1 is 10, and then I distribute to that term and that term, in which case I get 10 VA minus 100, and then I can distribute to this term and that term after reducing. So 10 divided by 5 is 2. So I get plus 2 VA minus 0. So I'll just leave it like that. And then the 10 I can distribute over here and over there after canceling with that 2. So here, this is going to be 5 VA minus 5 VB, and that's equal to 0. Then I can collect my terms. I have a 10 VAs from there, 2 more from there, 5 more from there, for a grand total of 17 VAs. And then minus 5 VB. This 100 I can add to that side, in which case I get 100. This is the first equation in my system. I'll call that equation number 1. Okay. So we use KCL at that first node. Let's go ahead and use KCL at this node. So I'm going to use KCL at node B. And the version of KCL that I'm going to use is the sum of the currents flowing out of this node must set up to 0. So at this node, we have some fictitious currents again. We have a current flowing through there. We have a current flowing out of there. And then we have a current flowing. Let me move it to the opposite side. It's a little bit clearer. So we have a current going out this way. So let's go ahead and take care of this current first. It's starting at node B, going to node A, going through the 2 ohm resistor. So here for that current, in terms of the modified version of Ohm's law, we have VB minus VA over 2 ohms. So this current is this one. Then we have another current. Let's concentrate on that one. It's starting at node B, going down to the ground node, flowing through the 10 ohm resistor. So here we have VB minus 0 volts over 10 ohms, like so. And then this last one is a little bit tricky, not the most tricky thing in the world, but a little bit tricky. Remember, we have assumed that all of the currents happen to be flowing out. And we have 2 amps that happen to be flowing in. Now, one of the things that you can do is I can reverse the direction of this current, but in reversing the direction of that current, I also have to change the sign on the current. So we had 2 amps going into that node. That is equivalent to minus 2 amps going out. So into KCL, we have minus 2 amps. Those are all the elements at that node. That must add up to 0 like so. Right? Now, notice that doing this physical change like this is a bit cumbersome. One of the ways in which you can actually just kind of remember that is if you happen to have a current source that happens to be forcing the current in KCL, all you have to do is remember, let's tack on that minus sign. Now, once again, we're faced with an equation with some fractions, so let's get rid of those and then collect terms. So I'll multiply everything through by 10. 10 divided by 2 is 5, and I can distribute. So this is 5 VB minus 5 VA. For the next one, the 10 cancels out cleanly, and I end up with plus VB. And then I have to multiply 10 by 2. That's minus 20. That adds up to 0. I have minus 5 VAs there. So minus 5 VA. I have 5 and 1 VBs there, so plus 6 VBs. And then this minus 20 I can add over there to the opposite side, in which case I get positive 20. I will call this equation 2. So let's write this out cleanly. We have a system of equations. Equation 1 is 17 VA minus 5 VB is equal to 100. And then equation number 2 is minus 5 VA plus 6 VB, and that is equal to 20. Now, here, what you would need to do is, for the system of equation, you need to solve this. Now, this is an electrical engineering class, not a math class. So I threw these into a calculator previously. So using a calculator, one of the things that I found is that VA had a value of 9.09 volts. and VB had a value of 10.91 volts. So you can verify this. I'll leave that as an exercise to you guys. Now, this is not the end of our problem. Why? Because we weren't looking just for VA and VB. We wanted to know what the current was through that 10 ohm resistor. So one of the things that we can do is I'm going to go back up to my original picture here. And I can say that my node voltages, and I'll do this in blue, at node A, this was 9.09 volts, and VB was 10.91 volts. So that's what we found mathematically. Question is, what direction is the current going to flow in? Well, current always goes from high voltage through a resistor down to low voltage. That means that the current flowing through the 2 ohm resistor has to go that way. Has to. There's no other choice. That means that I can also use my modified version of Ohm's law. So the current flowing through the 10 ohm resistor, well, it has to be VB minus VA divided by the 2 ohm resistance. And that is 10.91 volts minus 9.09 volts divided by 2 ohms. And you can throw this into your calculator, and what you should end up with is this is a current of 0.91 amps. So finally, the current flowing through the 10 ohm or the 2 ohm resistor is 0.91 amps, and it's going from the node that we labeled B all the way down to the node that we labeled A. This will complete this example. In the next example, we will talk about how to deal with circuits that contain dependent sources.